Well, we've heard yesterday something about Euclid, and I want to introduce you because there are several talks following this one going in a bit more detail. And so Euclid is a mission to really address some of the big questions in cosmology, and like we're talking about information. Well, it's nice to have a lot of information, but in a way in cosmology we're in a rather strange situation that for the longest time we sort of like the measurements were following the theory, but we now are in a situation that we now know that our current theories must be incomplete, right? It's not per se wrong, because they fit all the data we have, except that we know we miss a theory for some of the big open questions. So sometimes a lack of information can make you feel more comfortable. Right, so we know that we're wrong, which is a rather unique situation in science. And the reason we know we're wrong is when we look at the contents of the universe, like basically a large fraction of basically what we're required to explain the observations requires components that are not described by the standard model of particle physics. So it's cold dark matter, dark energy. And so that's really drives a lot of the research, right? So it's we know 96% of the universe we don't have a theory for, but we know, we're quite convinced that there must be something. So whether it's really dark matter, dark energy is sort of separate. What is clear, we need new physics, right? So the standard physics is not sufficient to explain these observations, which have gotten better over time. So how we divide up this pie is well established. And so that's, from an experimental point of view, makes life very, very difficult, because how should we research this? Because we can sort of say, well, we stick to a framework and improve the measurements, but that doesn't necessarily lead to a new theory because we stuck to a certain framework. We just constrained that particular model better. But what if it's the wrong model, right? And I think that is a challenge from if we want to sort of get better measurements to guide the theoretical development, we really need to understand, like, well, we need to keep our options open. So that's why I like this quote, right? It's very hard to find a black cat in a dark room if it were walking around here, especially if there is none, right? We would be searching forever, never sure where the cat is. And so then when we look at studying dark energy, because that's the main motivation for this kind of research, is like we need to investigate, okay, what should we measure? So I think that's right, we want to make measurements, and I think one important aspect, so we sort of can look at this from a little bit away, and so we need to see what we're sensitive to. Where does dark energy and dark matter, where do they leave signatures? And so one option is to look at the cosmic expansion history. After all, this is how dark energy was discovered, by looking at how does the universe expand and how does it change over time, right? People were looking for deceleration, so the universe, the expansion to slow down, and then 20 years ago, the big surprise was that it was accelerating. And that's usually quantified by this dark energy equation of state, this W, which could be a function of time. Right? So cosmological constant would be just -1 constant. But generally, this could be a function of time. But you could also look at the history of growth of structure formation, because right, as the universe expands, there's gravity trying to pull things together, and that balance between gravity pulling things together, so forming large-scale structure, and dark energy trying to pull things apart, that balance we can study, and that's what is quantified by this growth rate of structure. And what is important that you would like to do both, because if you just focus on this, then you will never learn anything if the problem was with gravity, right? Because after all, we're applying the theory of gravity, which is well tested in the solar system, we're applying it to cosmological scales. And so the key thing is that we really need, because currently there is no good theory that satisfactorily explains all these results, and so we need to improve the measurements by at least an order of magnitude, if not more. And that's difficult because the effects of dark energy are subtle. Because there's a reason why it was discovered only 20 years ago, even though it makes up most of the universe today. Right, so this is basically an update of the original discovery. So this is sort of I guess it has improved a little bit over time, but from a couple of years ago, the measurements of all the type 1a supernovae as a function of redshift. So really now it's well established that the universe is expanding at an accelerated pace. And these measurements have gotten better over time, and also having a lot of data allows you to sort of deal with worries like, is there dust in these supernovae, et cetera, et cetera. So the more data you get, which is, because people sometimes forget, is that, okay, well, there might be systematics, but the more data you collect, the better you can test systematics, and eventually you can essentially learn all possible problems that you put in. And this is now well established, except, as I said, like there are people that sort of study modified gravity theories, and they will always fit because they're degenerate with the measurement. So basically, if we look at sort of dark energy parameters, there's something called the figure of merit, how well parameters are constrained. This essentially has a formal figure of merit of 0. Right? It's a very useful measurement, but it doesn't constrain anything by itself. You need something else, could be CMB or other measurements, to really test the theory. Right, but as I said, also the dark energy changes how structure grows in the universe. And so as the universe expands and gravity tries to collapse, so we've seen things in simulations, of course, then the structure, so the way the structure evolves depends on the amount of dark matter and dark energy. And so we can ask, like, is the problem here? And yeah, the whole Einstein equation doesn't come out very clearly. That's 8 pi g over c to the 4th t here. But the question is really, is the problem here? Right? Is it a cosmological constant? So is it really something on say, vacuum properties? Or is the problem here on modified gravity? And we'll hear more about that as well. Right? We really want to test both. And so what we need to really do these measurements, right, is high precision. So we need a large survey, but that's clear. We need a lot of data if we want to measure this, because the effects are subtle. We need to beat down the error bars. But right, and people often talk about precision cosmology. That's sort of easy once you have a lot of data, but what we want is accurate cosmology, right? This is the challenge, is to high accuracy, to use all that information and actually extract useful information. Just a lot of information doesn't mean it's useful, right? And right, we look at the World Wide Web, there's a lot of information, but a lot of it is not very useful. And so how to extract that useful information, I think, is an interesting challenge. And when you look at these probes, they should also complement each other, because you can do very precise measurements. So this is what the supernova show. They're very, very precise in one direction, but they don't really tell you by themselves. So you want complementary probes. Of course, they should also allow for tests of systematics. And in particular, right, we need to keep an eye on, right, whether there is a cat or not, so to be able to also be sensitive if the problem is with gravity. So we really want to test many, many aspects, if possible, at once in the current paradigm. And so if we then step back a little bit further, then we can ask, like, what does that mean really? Well, so we basically, right, we see this change and expansion in the universe, so we want to see the evolution of the universe. And we also know, although this is not a guarantee, but at least we've seen that dark energy is important at low redshift. So this dominates at low redshift. So that's why you want to complement the CMB. And then if you look at general relativity, there's a time-like and a space-like potential, which in GR are the same. So that gets you the factor 2 when you do gravitational lensing. But in principle, in modified gravity theories, they are not necessarily the same. So you would like to decouple both of them. And so that allows you to distinguish between dark energy and modified gravity. And so if you translate these sort of requirements into what you would like an experiment to do, so you need redshift information. Otherwise, like if you don't have distance information, you wouldn't be able to see evolution. And because you want to be at lowish redshift, you want to be sort of out to redshift 2, right? So the CMB doesn't tell us much about dark energy, because it's a great anchor point, but it's sort of measures things when dark energy wasn't important. And you need 2 probes at least, because you want to disentangle this. So and they should be sensitive to the expansion history and the growth rate, but also very importantly, one of them needs to be a relativistic effect. And this is what Euclid aims to do. And I guess René Laurijs will talk next a bit more about the details of the mission. So I'll just focus on what we focus on in Leiden and also in Groningen, on the weak lensing by large-scale structure. But this is really an amazing project. It'll measure shapes of about 2 billion galaxies, will image with roughly Hubble Space Telescope resolution about a third of the sky. So it really is a tremendously rich resource. We'll do some infrared imaging over that same area, and that infrared imaging by itself is actually quite phenomenal for various applications. And there's a large number of spectra. So it's really a major improvement over the data we have by now, by at least an order of magnitude. But also not only in quantity, but also the quality hopefully should be better. And so the main probes, right, I'll focus on the lensing, but the main probes are galaxy clustering and gravitational lensing, and that's a very nice combination. If we sort of go back to what we want before, because the lensing gives us measurements of the dark matter distribution over time. It's sort of this redshift range, and it measures the sum of these potentials. And for that we need very good shapes and also multiband photometry to get the redshift information. Whereas the galaxy clustering probes the clustering history of the galaxies and gives us an estimate of this psi. And so combined with lensing, we can sort of disentangle the two. So that's very powerful. But also what is nice is that so they complement each other as a probe, as a measurement, but also they require quite similar areas of sky. So as when you put them on a single telescope, and our chair I think is partly responsible for that idea, because initially there were two projects, and so that was a very good idea to put them together, because they, from a survey perspective, they complement each other very nicely as well. Also the infrared imaging helps with the spectroscopy, etc. Right, so but what my work focuses on is this particular probe is how can we see the clustering of the dark matter, because of course the dark matter is invisible, and yesterday in the dome movie you saw already it was exaggerated, this sort of lensing screen in front of these galaxies sort of for this distorted view of the distant galaxies. And so that was exaggerated, but that effect actually occurs. So when we look at the sky, we see a slightly distorted version of the sky, and these distortions, they lead to coherent alignments in the shapes of galaxies. And we can try to measure this. And this was also shown yesterday in this movie about the hunt for dark matter. Right? When we do this and measure these shapes, we can make a picture of the dark matter distribution. For instance, in this well-known bullet cluster, or this is another cluster I've worked on. And so we can actually make an image of the dark matter distribution, and also Edwin yesterday showed them nicely on the dome, right? So these are really pictures of something you cannot see, because we can reconstruct the dark matter distribution by measuring the shapes of many, many galaxies. So you can look at clusters of galaxies, or we can just look at a random piece of sky. And so this is, right, if we now have redshift information for the sources, so we can sort of say, okay, this source is here. You can sort of think of this is not exactly how you would do the actual analysis, but you could say, well, let's take sources at sort of low redshift, then they tell us something about a mass distribution at even lower redshifts, and then you go to higher redshift, and then you say, well, I know already what was here, so the difference must be the stuff at intermediate redshift, and etc. And so that allows us to slice up the universe and reconstruct how the growth of structure, how structure changes over time. And so this requires then redshifts for the individual sources, and unfortunately we don't need very good precise redshifts, but we need photometric redshift, which still, like, it makes life in a way easier, but also harder, because it's very hard to control this. And so then, it's like if we look at Euclid, right, it's clearly a lot of data coming our way, but I would say it's a lot of potential information, because this is not about amounts of data, but it's about control, like careful control of systematics. Because the raw data, yeah, it'll look great, and for many applications that's all you need. But for us, essentially, we want to average 2 billion galaxies and sort of guarantee that the square root of n reduction in uncertainty still works. So it's potential information. And to just give you a sense of what we're trying to do, we're trying to measure the change in shape of the Earth and the Moon, because that change in ellipticity, because the Earth spins a bit faster, is about 2 parts in 1,000. And that's roughly our requirement. So we take all these galaxies and we sort of guarantee that we measure on average the shapes to 2 parts in 1,000. Like, there's no way you can see this by eye. So that's the problem. We do a measurement, and we have no way of telling whether that measurement was done correctly on an individual galaxy. But in an ensemble, we can test this. Right? So we really we need to assume that or guarantee that the measurement is accurate. If that's not the case, that's it. Like, we can't do dark energy measurements. Right, and so we can then look at, so how would you design a survey? Well, you can, so first of all, you sort of say, okay, we want to measure dark energy properties, so we want a certain level of systematics, of statistics, right? So you basically define the probes, that's what I did earlier, right? So lensing and clustering is very nice. You want roughly a third of the sky. That gives you interesting sort of constraints. And then that tells you sort of, what area and depth you need. Right, so you say, okay, now I want to measure this, I want to measure it with that precision, so that defines the survey. So this is sort of what defines the precision, but then the hard part, which is basically keeps us busy for already 7 years now, is to make sure that these measurements are accurate. And that really derives the design of the instrument. That's one of the reasons why we go to space, and calibration. And the challenge is that as you go down, in this flow down, information is lost. Like, right? You have to write something down in words, and these words do not describe necessarily exactly what is done. And in particular, when you've originally designed this project, you don't want to drive it in a particular direction, so you keep it rather general, and that's where information is essentially lost. It's not per se lost, but it's not the most precise description of what needs to be done. And so that was very useful, because that allows you to sort of say, okay, this may be more important than that. But at the end of the day, like, all these bits and pieces have to come together. So this helps you to prioritize the development, but it has shortcomings. For instance, in reality, like, the survey strategy matters. It does matter to some extent where you start looking, how you, which order you do the observations. Systematics act on particular scales, right? They're tied to the detector, etc. So in the original approach, when you do this flow down, this is the kind of information that gets lost. There's no way of capturing this in a way that doesn't define the survey itself. And also systematics are independent. In reality, there are correlations between them. And so you can show that actually in general, that the result is that when you start this way, that you end up with something that is rather conservative, or at least if the way we've set it up was rather conservative. But what we want to do now is actually go back and actually see how much information is there really in the survey. And for that, you want to simulate the actual survey. And so we'll start with doing also combining the measurements of the different probes. And so there's a Euclid flagship simulation, which is really an amazing resource for the consortium. It's a very large record-setting computer simulation. It's 2 trillion dark matter particles, so it's not a hydro simulation. But it's more than 2 billion galaxies in there. So it really allows us to sort of have a realistic starting point for the survey. So this is what it looks like on my screen, and it should be possible to also show this full dome. So this is the simulation that we base our analysis on. So, and it really, well, this is half the sky, so just cut out a little bit of this, and that's what Euclid observes. Right? So that gives you an idea of the richness of the data that we'll see. And of course, there's a lot of work going on, right? Because for now, we're mostly focused on transforming this into a power spectrum. But clearly, there's way more information in there in this image than just the power spectrum. So that's actually also ongoing research to see how can we learn more about this. So let me continue to sort of the next step of how we do this. And so basically what we do in this flow up, so we're now going from the bottom, we sort of know how the survey works. We sort of propagate things up. And so we take advantage of the fact that our building block, and this is different from the galaxy cluster, our building block is the shape measurement of one galaxy. And so at best we care about maybe there was another galaxy nearby. But we can split up the whole process and build up essentially what is similar to a Bayesian hierarchical model and sort of move our way forward. So we can start with input galaxies from this flagship simulation, so we have realistic properties of the galaxies, and work our way to fake measurements and sort of perfectly correct that, and that gives us the perfect signal. and we can perturb the systematic. So we can sort of say, well, we correct this, but there's uncertainties in how well we can do. So that's where we can fold in requirements on calibration. So this is really an abstraction of what the survey does. And it's actually a very powerful approach. So it really allows us to put in things step by step, so we can either make assumptions about what is happening there, or we can put in more detailed modeling that is going along. And eventually, as we go along, we get an ever more realistic estimate of the performance. And so what we're working on so far is looking at the realistic layout, so play with the survey, a really realistic PSF itself, so that the smearing by the telescope optics can be done now in a realistic way, and we can account for the radiation damage due to the fact that we're in space. And so there's various next steps. But this gives you an idea of, by just looking at what residual power spectrum does a particular systematic introduce, and this is the point spread function. And so when we did the original requirements, we did not have a complicated curve. Like, it was just a flat line. And you can see that the fact that this is a line with more structure allows us to actually disentangle this much better from the cosmological signal. So basically what we're gaining, and this is why the older results were more conservative, is that typically cosmological parameters do not have an effect like this, and so we can sort of project out their contribution to the residual power spectrum. And so this allows us to really update the precision we need to calibrate things with. And so this is very powerful. So it's very flexible, and so we need to do more work. But I think in the end, there's really also some of these studies that we need to do, because we can now home in on interesting questions. They are interesting in their own right. Right? But so let's assume that we can all solve this. So clearly, right, instead of potential information, there's a lot of information. So just in the last minute, I want to talk also a little bit about other things we can do. So it'll be phenomenal for strong lensing studies. So I focus on what we call weak gravitational lensing. But right now, there's a sort of few hundred of these strong lenses known. Euclid will increase that to about 300,000, right? So you can do population studies. You have to rethink how you can do the modeling. Now you could say, oh, I like this lens, I can spend a month modeling it. Like, you can't afford, well, there will be still very special cases with multiple lensing events, which doesn't come out very clearly here, but it really will transform that field. Just to sort of as a sort of take-home message, right? You're probably all familiar with the Sloan Digital Sky Survey. Euclid is sort of, in a nutshell, the equivalent at redshift 1. So it really allows us to sort of take all that stuff that was done with at low redshift and say, well, what's the anchor point at high redshift? So this gives an idea. This is M51 at low redshift, sort of seen by Sloan. We would see it with similar quality at redshift 1-ish. And of course, at redshift 0.1 at the Sloan redshift, we would really resolve this. So that's a really rich data set, not only for cosmology, but for essentially all aspects of extragalactic cosmology, also a nice complement to Gaia. So just to end, so I think Euclid will be a really important step forward for testing our current paradigm. So really, what is the nature of dark energy, but also inflationary parameters, testing modified gravity. But it's not limited to that. So I think it'll really impact many. It will be the starting point for many other studies in extragalactic astronomy. And if you want to read more, of course, this is already a bit old by now, but it does sort of sketch some of the science we can do with Euclid. It's this reference here. Thank you.
Thank you, Henk. Any questions?
You mentioned that the simulation from Joachim Stedo is hydrodynamics.
No, it's not. It's not. It's just
purely
yeah.
quantum matter. I just wanted to
Yeah.
make sure. Thank you.
Yeah, we wish it would be a hydro, but it'll be a little while away.
Not impressive as that full dome picture was, of course. You could give it in 3D as well.
Yeah, yeah.
I'll give you this one.
Yeah, can you say something more about the systematics plot that you showed? It seems like the systematics are much larger than your intrinsic error bar. Is that right? Is that what it published?
Oh no, so this is, yeah, so this is basically what we can do. We can do many realizations. So what you want in the end is not so much the error on that curve that we had, but so it is tied to sort of how the systematics were phrased, because right now they're sort of numbers. But so what does it mean that you have your PSF has to be less than some number? Does it mean 3 sigma, 5 sigma, never? And so we can also now approach sort of Monte Carlo way and say, what are the distributions of systematics? And sort of say, okay, the requirements, like we know there are PDFs, and sort of say, well, actually when we combine all these PDFs, this is all fine. So it really is a mechanism to say, given what we know about the current design, is it sufficient, rather than having clear-cut numbers? Because if you do always 5 sigma, then really you're way too conservative, right? So you should say, well, sometimes it can be a bit higher, but in other systematic can be a little bit lower. So those numbers were sort of the uncertainties on when you look at many realizations, and then the overall curve indeed is the overall systematics that get induced. So you want to sort of limit that as well, or we want to know the knowledge of that. You can also say, well, if I know what that curve looks like, I can correct for it.
I see. So you're using the various simulations to address, but you get an error bar on that. As long as
Yeah.
it's smaller than your systematic, you're okay.
Yeah, or at least we can sort of say by how much because one concern is that systematics might be really unconstrained. Right, so then you would be worried. So you might naively think that you're fine, but in reality there's some instability which allows you to vary that quite a bit. And so this approach allows us to also explore that. So it's like how robustly can we do this? So if you take one realization and you take another realization of the same, essentially the same telescope, like how confident are we that that systematic is estimated correctly?